we'll talk about battery waste management from electronic vehicle. The guest speaker for this topic will be Professor Dr. Rungsima Yeetsorn. She's the Deputy Director in Administration and Innovation Management of the King Mongkut University. We will cover today. We will talk about battery waste management from electronic vehicles. The point I like to touch upon are: why do we need battery waste management? We look into options for battery waste management, what the options are. We'll look into two main areas. We'll look into second life battery and battery recycling. With the battery recycling, we will touch upon that, and we will talk a little bit about electrode recycling. So that's the topic for today. First, we'll start off with what is the HEV, with the hybrid electric vehicle, the type of EV cars. Just to sum up, there are three kinds. The first kind is hybrid electric vehicle, or HEV, which we use the ICE engine to be used outside in urban areas. Here are the examples of the hybrid electric vehicle, which will help to recharge the battery. The second will be plug-in hybrid electric vehicle, or PHEV. We use a no battery charging system that can be fed externally. Here are the powertrain, the difference between the hybrid and the plug-in hybrid. The third point is the battery electric vehicle that we mostly talk about, the BEV. Here are the main battery usage. There's no oil tank within the vehicle. Now the fuel cell electric vehicle. With the Tesla, use the battery electric vehicle. But with the Toyota, mainly, they give quite interested in the fuel cell electric vehicle. And the last but not least that we not talk about much is the solar electric vehicle, or SEV. This is the vehicle that we use the solar cell mainly. However, with this type of vehicle, it is necessary to have the battery control unit and the power converter within the vehicle. This is the comparison, the major available for the advantages and the disadvantages. Between the advantages and disadvantages, but between different type of electrical vehicle. So of course, there will be cost and weight and a zero emission. the infrastructure are also the main point that we're trying to support about the charging station. We have the cooperate between the government organization. However, with the FCEV, it's not quite popular at the moment, especially in the Southeast Asia. We still have problem with the hydrogen generation on board because of the high cost. So the most popular that used widely is the battery electric vehicle or BEV. Currently, there are two main types of BEVs. There's two types. There are nickel-metal hybrid, which is used in hybrid EVs, and the lithium-ion batteries, which used in plug-in EVs. So with those two types, there's three main things that, to sum up, the first is the density of energy compared to the weight with the lithium ion. The other topic that we haven't touched upon are the memory effect.
As we see the picture, 100% we charge, but to use it only 70%. Comparing with the same capacity, lithium ion has higher performance. For example, nickel metal hydride, there is self-discharge 50%. If it's lithium ion, average self-discharge 0.1 per day. So it's too small. The battery that is very hot nowadays, basically they care about the weight and energy density and memory effect, and also the sudden death. We need to see the driving behavior, which cause the death of battery. There would be the test and see the behavior of driver, maybe how they speed up or over speed. This could cause the chemistry reaction or the energy distribution. This could cause the diversity of death materials. That's overview. Talking about why we have to care about the battery management. Look at the graph. This is the Thailand market in 2000. From now on until, this is like until 2020 of EV market. whether two wheels or four wheels or buses, 70% in the last 2 years, the average of growth of electric vehicles is so fast. In 2020, it's 190,000 cars. Basically, PHEV and HEV for BEV is about 3,000 vehicles. It's more than half of growth comparing with 2019. Comparing the world or global growth, it's 145 million EV around the world. So when we take a look, if you develop EV, that means the battery, good battery would be required as well. The material to use. So we'll discuss about IEA. They give us the information. Dead battery since last year is 180,000 metric tons per year. 180,000 metric ton was the recycling battery, but the rest is 500,000 metric tons. In 2040, they expected that recycling will reduce mineral demand. Nowadays, it's 5% only of mineral demand. This would satisfy the demand of the resource. The mineral that we use, what's the lithium, nickel, cobalt, that is the main mineral from Russia. When the war occurred, we have problems, but Indonesia, many battery makers invested in Indonesia. Also in Africa, they have the Congo. Comparing with many countries around the world, we have the main resource in 3 countries. So we have resources problem. What about the average of resources? Take a look at electric vehicles. Use different minerals. They use 75 kilowatt hours as the battery pack. So look at the picture. This is how they use the minerals. The graphite is not taking seriously in recycling. It's the stable technology. Look at the statistic. Graphite, lithium, nickel, and cobalt. The average of the demand from now to 2028, the growth is 1,000%. except cobalt only 452%. That means we have the same resource, but the needs of battery productions is high. Don't forget that we produce the battery for other facilities as well. Lithium is in different resources according to the map. Around our area, Southeast Asia, we do not have them. But lithium per year were produced about 80,000 tons. The demand nowadays, since 2020, is 1.5 tons. That's the main problem. It's the resource problem. So when we take a look at the battery maker, China, Japan, Korea, they are aware of this problem. They pay attention on waste management. Since 2022, from now on, they can manage the waste for 500 tons to 1.2 million tons. Right now, there is the rapidly growth. After the COVID, the red graph, the demands of lithium would be pretty high. This caused high price in China, Korea, Japan, more than 7 times. So the resource cost high price, and it costs how people use EV in the future. When we take a look at the resource, if we need the resource, it's from the mineral factory, the needs of the water use, the chemistry, leak, some of the mineral component would be important, that we need to be aware that we cannot increase the mineral factory. Look at the circle graph. I want to see different components of battery: electrolyte casing, anode, the part that we can recycle is lithium, cobalt, and magnesium, nickel. The metal, the different type of metal, the copper, aluminum, and graphite. And different cases, that's steel and metal. But the ongoing problem is plastic. The separator changed from paper to plastic, cases and binder made of polymer and plastic. Even it's the small proportion to recycle. But how can we do the waste management? So the world see this problem is on the risk. How to bring the raw material if the mineral is not produced, lithium, cobalt would be the high risk. Aluminum is risky to lose. Manganese, nickel, copper, and graphite would be the middle risk. Technology can solve all the risks, especially the mineral that has high risk. They will develop that first. They cannot cover as a whole. It's difficult to cover all the risk. Besides, look at the number of battery that we can recycle and waste is different proportion. The resource is still complicated, and it's the waste energy. It's just like it's not worth of money. With the environment, if we don't manage it, we have to find other technology, but this would be the solid waste. If we trust it in the soil, it would be the leaching and would be poisoning to the water, and probably they have to burn out. And if it's not in a proper method, it would produce the poison gas or toxic carcinogen, just like in the picture. It can dilute in the air and it could cause emission. As it review, they crash the components of the battery, as similar as the circle graph. Combine the metal and other materials. If it become the dead form, it would be the gas, liquid, solid, and it would be on the different route. If it's toxic, basically it causes us how we breathe. So it come from different from soil and mixed with the water. The full battery, the flow battery, is one of the choice. Flow battery will fleet the electrolyte and collect electrochemistry or electrochemical reaction, and it could store electricity. Electrolyte is still the problem. The recycle or the vanadium, they try to manage and make it less toxic and try to cover 97% of vanadium. But So they can use it as a charging stationary. How do we know it's the end of the battery? So did we talk about the life of the battery or the performance, the capacity or internal resistance? Look at the red lines is the capacity of the battery. If we recycle 80%, if the battery perform the performance 80%, they will not use it, but they will use it. They will make it a second life. They can make it direct recycling, and it would cost more or value more. BMW talk about other application like energy storage or for alternative resource. After that, the percentage of the performance, it will come to the battery waste management or remanufacturing.
So there's an option for battery waste management. There's two waste management. Firstly is recycle and second life. Let's talk about recycle first. So from natural resources, there's a process through until disposal. The natural resources, when it comes to end of life, we will reuse it again, so it go into circle. However, with the second life, if you look at the green circle, it start from recycle, then the battery cannot be recycled again, so we look into battery refurbish. I will go around and repetitive the cycle again. So now there's a cons and pro of the second life battery. There's many factors. For example, cost. The cost is there will be half of the price of new batteries. But what I want to mention here of the second life batteries is the cost. Well, at the moment in China, the reused battery are more expensive, are become quite expensive. So that's what we try to look upon on because of the lack of resources. Also, we don't have no standards. There's no standards to show down the industrialization of the LSB. So now what's the challenges? I like to sum up. Here are the challenges to identify for each individual step. The first point is the human aid operation. This is the reason why it's quite high, so that make the battery become expensive. Secondly, lack of standardized indicators and models. We need more understanding of the mechanical integrity inspection steps. We need more research on driving behavior of the vehicle users so we can use and select the material accordingly. And thirdly, there's lack of or the absence of high efficiency algorithms. With this slide here, we'll touch upon on the research document on the end of life or second life options for retired electric vehicle batteries. This is the 4 of the 5 options. The life cycle of lithium batteries. Of course, with the disposal, so if the battery is out of order or out of use, we can dispose of it by destroying it, or we can recycle it. Or if we restoring, then we use each part of the battery and adapt it. Or we reuse it. For example, if we can't use it for the high efficiency use, then we can use it for the backup power or home use instead. Or we use it for alternative energy, for solar cell or fuel cells.
The options that they use, there are 5 types, 5 options. I have to talk about 4 options. First, disposal. We just throw it away, but we need to make it appropriately. We cannot control all the houses, so this could cause hazardous leaching. Incineration could release the toxic gas. The electrolyte could produce hydroxide or different substance from the metals or materials. That is a little complicated. Recycling is one of the technology that people choose. So they use physical material separation, and this would be the process of chemistry. refurbish or restoring. Is to disassembler to see and restore. They would see the surface if it's still workable. For example, they would see the electrolyte or the component that is not. As far as the options for applications, I will not talk about, but we'll talk about the backup power, low speed, the refurbish, we still have problem, how we collect, logistic, testing on electrical chemistry, so we can know the difference of application we can use. Lithium-ion batteries, if they have to use it, step 1, they need to check after getting the battery if it's in a good quality or not. Is diagnosis to categorize. This is the whole process. They need to see the open circuits resistance. They need to check the capacity. This process is IES as a part of the process. They will evaluate the whole picture. Regrouping is when you pack a lot of battery, it doesn't mean that it would have the same grade. Depends on what works you would use. Some battery would be dead, but you need to be selective. This is the information from the makers that they use the second life of the battery. They need to analyze. So they have their important projects like Nissan company or Europe makers or Renault or Japan makers. As a pyramid, they have the wider base. This is the sample from Nissan list. Probably the battery was already dead, and they used some and some. They use it as the part of the vehicle component. The lifespan is about 10 to 15 years. After recycling, they can still use it for 8 years. This is from Nissan, and here is from Europe, Volkswagen. They use the repack battery. It's Volkswagen Passat. They use it to recharge buses. This is one way of reuse of the second life battery. This is the number for you to redesign the battery. This is the process of recycling. Look at the graph, you would find the demand of using the recycled battery is not even 500,000. It's 1.5 demand of using lithium. Dr. Manov said that we use the cooling or thermal system. We try to decrease the inner reactions of chemistry. So after we do cell disrupt, after we take off the cell, we need to dissolution to dissolve the chemist. For the physical thermal is to get out the materials. For mechanical process is crushing, and shredding, and drying process. But we need to be careful not to let it burning, and we probably need to then it would come to the apparently it has been worked on by many makers. For BMW, focus on lithium, nickel, cobalt, and graphite because it's high risk to be short. This is the battery pack from recycling. They have the Excellence Center in 2020. They have 2,000 tons production, and they wanted to produce it more. In Europe, the biggest plant is from Norway. So take a look at the number. This is Renault and Violine, the expertise of battery makers, also from China. In Asia is the over 500,000 tons. Southeast Asia we do not have the projects for recycling battery for cars, but we have in Singapore for the cell phone battery recycling. This is unpacked from different model. This is crushing process. We need to push the nitrogen to protect ignition. This is the liquid electrolyte suppression, and we'll get the dust or particle mixing with different mineral. And this is hydrometallurgy. They will melt and separate. This picture as a whole is the technology of the large companies. They have the same concept, but they have complicated technology differences. This is the first concept, is to use the heat. Second, use the chemist or hydrogen peroxide or direct recycle or reuse. This page is to compare the process differences, the technology that is very popular is to use biofossil. This is for the master graduate students. It's a picture as a whole, the possibility of conducting the research. This is the collaboration with Arken. This is electrode recycling. If the battery would be able to mix with the water or not. So they probably use the different chemists. They cannot use one substance to separate all chemists. They need to use proper chemist to separate substance. Can they reuse the chemist and try to avoid the implication to the environment?